Trigonometry, Chapter 6, Inverse Circular Functions and Trig Equations, Section 1, Inverse Circular Functions, Video 4, Using a Calculator to Evaluate Inverse Trig Functions. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we determined the domain and range of the remaining inverse trig functions. Here's a summary of all of them. As we move forward, we will be focusing more on the quadrants represented by the ranges and not the specific ranges themselves in interval notation. In this section, we quickly discuss calculator usage for inverse trig functions, because not all calculators are created the same. As usual, the first thing you should check is what mode your calculator is in. Although we frequently discuss radian measure for angles, degrees are still an option. Which mode you need depends on the problem at hand. If no mode is mentioned in the problem, always assume radians. Got it? If a calculator has trig functions, it sometimes only has sine, cosine, and tangent. As such, it sometimes only has sine inverse, cosine inverse, and tangent inverse. Now, if your calculator also has secant, cosecant, and cotangent, and their inverses, you can skip the rest of this video. Otherwise, you have to know how to use the trig buttons your calculator does have to handle the trig functions it doesn't have. Now, by now, you should know that reciprocal identities can be used to evaluate secant, cosecant, and cotangent. For example, if you want to find the value of secant of pi over 7, you would evaluate 1 over cosine of pi over 7 in your calculator if you don't have a secant button. But what about something like secant inverse of 1.6? To evaluate the inverse of a reciprocal function, secant, cosecant, or cotangent, think about what the value is supposed to do. For example, to evaluate secant inverse of 1.6, let's let secant inverse of 1.6 equal k. That means that secant of k is supposed to equal 1.6. Remember how inverse functions work. Input of one is the output of the other, and vice versa. But secant is just 1 over cosine. So this implies that cosine of k is equal to 1 over 1.6. And hence, if we do inverse trig here, k is cosine inverse of 1 over 1.6. But k was secant inverse of 1.6. So if we equate these two inverse trig expressions, we get secant inverse of 1.6 equals cosine inverse of 1 over 1.6. Now from this, we could repeat the argument using a generic input for secant inverse and conclude that secant inverse of x equals cosine inverse of 1 over x for any value x in the domain of secant inverse. A similar argument would apply to cosecant inverse and cotangent inverse. Thus, secant inverse of x equals cosine inverse of 1 over x, cosecant inverse of x equals sine inverse of 1 over x, and cotangent inverse of x equals tangent inverse of 1 over x for all x in the domain of the respective inverse trig functions. So for example, let's evaluate some inverse trig functions, not sine, cosine, or tangent. And we're going to round to 4 decimal places as necessary. Let's think about how we would do this. We already talked about secant inverse of 1.6. It was cosine inverse of the reciprocal. So you could say it's the inverse reciprocal trig function of the reciprocal. Yeah. So for secant inverse, and we're going to write this first and then we'll expose the solutions. This is almost like a now you try, except I'm doing it with you or for you. For this one, we would say, well, the reciprocal of secant is cosine, so we do cosine inverse of 1 over 1 of the reciprocal. How would we set up cotangent inverse of -5? What is the reciprocal function of cotangent? Tangent. So instead of cotangent inverse, we would do tangent inverse. That's a horrible looking A and N. My thing's just getting larger over here. And then when we take the reciprocal to get -1/5. What about for cosecant inverse? Well, cosecant is the reciprocal of sine. So instead of cosecant inverse, we would do sine inverse. inverse. And then the reciprocal of 2 is 1/2. So that would transform all of these from problems that some calculators can't handle to problems that some calculators can, but that's how you would do it. And we would put them in a calculator. But did you recognize the last one was an exact value? The sine inverse of 1/2 is exactly pi over 6. You can put it in a calculator, and your calculator may tell you pi over 6 if you have a fancy enough calculator, but most likely it'll tell you the decimal version of pi over 6. If you know the exact value of a trig problem, you should give the exact value. Now you try. Evaluate, round to 4 decimal places necessary. Pause the video, give it a try. Remember, we're writing each inverse reciprocal trig function. And try that again. We're writing each inverse trig function in terms of the reciprocal inverse, the inverse reciprocal trig function. Not quite sure the correct order to say those words in. Anyway, give it a try. Here's your fair warning if you haven't paused the video yet. Solutions of 3, 2, and 1. How many of you tried to evaluate the first one? It was a trick question because 0.6 is not in the domain of secant inverse. Don't believe me? Secant inverse, domain is everything except between -1 and 1. 0.6 is between -1 and 1. Tricky, 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 but you know what? It's all fair game. Cotangent inverse of pi was tangent inverse of 1 over pi, which is about 0.382. And for cosecant inverse of -2 squared of 3 over 3, we do sine inverse of the reciprocal and then rationalize the denominator by multiplying both sides by the square root of 3 over 3. We get a 3 on the bottom that cancels the 3 on the top, leaving us sine inverse of -square root of 3 over 2. That should have jumped out at you as a unit circle coordinate. Sine inverse of -square root of 3 over 2 is -pi over 3. It does have to be -pi over 3 in quadrant 4. It can't be 4 pi over 3 in quadrant 3 because the range of sine inverse is quadrants 1 and 4. And that's the end of that one.